Hello everyone, I am Dean. I am going to present our paper called Coherent Detection of Entities from Images with Multiple Modalities. In this paper, we have shown an approach of information extraction for entities from PDF pages. The information extraction for various entities has large application. In our case, entities are the different product information blurb present on the seller PDF page. One PDF page has different entities layouts along with their image and text counterpart. Accurate information extraction for these entities demands separate detection of these entities, which is a challenging task. An easy way to solve this problem is to treat the entity layout as object bounding box. In this work, we predict each entity on a page. We leverage the object detection approach, but the definition of the object here is very different. The key challenges we face here is image and text alignment within the entities and the domain shift of the entities across the PDF pages we have. To formulate our problem, we constructed our dataset such that Di is each sample and is represented by a triplet set, where Ni are the number of entities within this Di. Here, I is the ith image and bj's are the bounding boxes of each entities within Di, and cj is the indicator whether these bounding boxes is positive or negative. Positive bounding boxes are the bounding boxes which encloses its entities closely, and the negative bounding boxes are the boxes which are random in nature and it can be anywhere in the page. It may include text from one entity and image from another entity. So we call it negative sample bounding boxes. Let Ti and Pi is the extracted text and 2D positional embedding using the OCR for image I. Now the objective is to learn the bounding box coordinate of entities for each image I. Our proposed model leverages deformable data. Deformable data is a transformer-based object detection model for unimodal objects. Deformable data contains two stages: a CNN-based model architecture for feature extraction and a transformer-based architecture for object detection. For input image I, we extracted the hierarchical features, and again for this image we have extracted the text and its 2D positional embedding using OCR. We join the two information, that is hierarchical feature and textual information, and pass to the encoder-decoder layer. The loss function of deformable data is a bipartite matching loss between the predicted and the ground truth bounding boxes. The matching loss is defined as the probability of likelihood of predicted class Ci given that it is not in the don't care region plus the bounding box loss. So all combined for all samples, it is a combination of log likelihood and the bounding box loss. Now, the bounding box loss is defined as the intersection of a union loss between the predicted and the ground truth, and L1 regression loss between the predicted and the ground truth bounding box coordinates values. There are two classes in our dataset: positive bounding box class and negative bounding box class. To overcome the confusion, if negative bounding box is assigned as positive, we put more penalty on it. So we come up a penalty loss, and it defined as the likelihood of the negative bounding boxes which are predicted as positive, and we add this penalty loss along with a regularization parameter to the total loss defined in the previous slide. Now the domain shift is a bigger problem in our case. Let's say we have an entity of a chair product in one PDF page. Now as the product varies along the sellers, the images are getting different and different. So there may be a case that there are some different entities of chair instances in our training set, and it may not have seen a different kind of chair instances in the test set. So therefore the domain shift is another challenge, and we leverage the gradient reversal layer and domain discriminator for domain adaptation problem. We have implemented state-of-the-art gradient reversal layer which can be illustrated as follows. and the domain discriminator is applied to each of the encoder-decoder layer. Here we describe the overall architecture for our model. For every image I, it goes to the CNN and gets its features, and it goes to the OCR as well to extract its text and 2D positional embedding. Now these two visual and textual features are getting concatenated and feed it to the encoder and decoder layers. The encoder and decoder layers are equipped with gradient reversal layers to address the domain adaptation problem. Now after the decoder, it goes to the bipartite matching loss sections where it goes to the fully connected layer, and it predicts the bounding boxes of positive and negative classes. So in this case actually we neglect the negative classes because we don't need it, and we only take the positive bounding boxes where it predicts entities which encloses both its image and text counterparts. To construct our dataset, we collected the samples from PDF catalogs from different brands, and dataset contains 52,000 bounding boxes where 26,000 is positive and 26,000 is negative. So on an average per page, we have 3 annotations for positive bounding boxes and 3.83 for negative bounding boxes. We report the results over the standard evaluation matrices average precision at above 75% IOU, and respectively the numbers indicates that, and average recall at above 75% IOU, and the rest numbers indicate the IOU numbers for the object detection. We also report the average intersection over union for the detection of bounding boxes with respect to the ground truth. Here we are presenting the quantitative results. As we are not able to report the absolute values of the matrix, we are reporting the lift over faster RCNN. So we can see that our method is performing best with respect to all the methods for every metric. Let's say IUs and average precision and recall values at different IU levels mentioned here. So the dash here mentions that the right hand side capabilities are not included in our method. So as you can see that without any negative sample, multimodal or domain adaptation, our method is equivalent to data. As we are adding more capabilities to our method, our matrix sees a significant jump over the different capabilities adding up. Let's say our method with the negative sample and multimodal sees a significant jump over the vanilla data, and adding the domain adaptation with the final one, we can see the best result. So we can, from here we can evaluate the importance of different capabilities, negative sample, multimodalities and domain adaptation in our method. Here we are presenting the generalization capabilities of our model. The left three categories are present in the training set, and the right three categories are novel, which is not at all presented in the training set. So as you can see that the right three categories are also able to perform as per with the categories which has seen in during the training. Here we are reporting the qualitative results. Our method is presented on the left bottom side, and we can see that our method is able to draw a tight bounding box enclosing the entities with respect to the other methods. In this ablation, we are going to see the importance of domain adaptation. We are reporting the relative IOs with respect to faster RCNN for all the methods. We are reporting this without any negative sample included in the methods, and adding the domain adaptation in the deformable data, which is represents our model on the top right bar, is actually we have seen that a significant jump. To summarize, we develop an automated system for detecting multimodal entity or information. The proposed multimodal approach helps to improve the model performance. Negative sample aware training strategy significantly improves the model performance. The domain shift is another challenge. The proposed domain adaptation technique handles the same. Thanks for your time, everyone.